So we said that non-executable pages stop some memory safety attacks, and the idea is if the attacker writes their own shellcode into memory, they are no longer able to execute that code, because all data is writable or executable, but not both. So if you write something into data, you cannot execute it. But that's not going to stop all attacks. In particular, what if the attacker uses code that's already there? If you already have code sitting in memory, that code's going to be executable. So for example, if you look back here, all the code down here is already executable. So maybe the attacker cannot execute code that they inject themselves, but they could still try and execute code that's already living in memory at a place that's marked executable. So the way we're going to try and subvert non-executable pages is we are going to try and execute code that's already there. And this turns out to be more dangerous than it seems at first, because when you're running a program, it's often the case that you don't just have the instructions of your own program, but you also have other libraries that you import. So that code section at the bottom of the memory layout, it might not just have the instructions that the programmer wrote, it might also have all of the C standard library functions, or any library that the user implemented. So there's all sorts of instructions sitting down there in the code section. And if the attacker is clever, they can try to get some of those instructions to execute and possibly cause some malicious things to happen. So that's what we're going to do to try and subvert non-executable pages. We can no longer write our own shellcode to exploit and run, but we can still run code that's already there. So we'll start with an attack called Return-to-libc, and then we'll make it even better with something called return-oriented programming. And we'll see each of these one at a time. But they both have the same idea, that is, using code that's already there to construct shellcode. OK, so let's start with the first attack called Return-to-libc. And so the idea here is there are already some C standard library functions that can do pretty dangerous things. So if the user imports the C standard library, one of the functions that they get is something called system. And what system does is it takes any shell command and executes it. So if you create a string that says rm-rf, which means delete everything on your system, I don't recommend running this command. But if the user defines a string like this, and they call system with that string as an argument, guess what happens? We open a shell, we run that command, and the entire system is deleted. So this is some code that already exists in memory. The attacker didn't have to write the instructions of system themselves. That code's already sitting there in the C standard library. So all the attacker has to do is redirect the program not to their own custom shellcode, but to the system function, and then pass in some malicious argument like this to cause bad things to happen. So that's why we call it Return-to-libc. Instead of returning to some shellcode that the attacker wrote, when the function returns, goes to the RIP, goes to that address, we are actually going to jump into some other function like system and cause bad things to happen. So here's an example of Return-to-libc in action. We have the system command sitting in the C standard library, and we have a vulnerable function that calls getS. Now let's assume that non-executable pages are on. So your standard buffer overflow attack will not work. You can't just overwrite RIP with shellcode and then write shellcode here. All of this stuff on the stack is non-executable. If you write shellcode here and try to execute it, the program will not let you do that. The operating system will stop you. But we have this nice system function sitting here. So instead of jumping to shellcode, what if we jumped to system? And when we jump to system, why don't we pass in an argument that causes bad things to happen? Because remember, where are arguments passed in? How does a function receive its arguments? On the stack. And what does getS let you do? It lets you write on the stack. So not only can we overwrite RIP to point to system, we can also feed in malicious arguments on the stack to cause system to do malicious things. So that's what we're going to do. And this is what the exploit roughly looks like. So let's take this exploit, let's dump it into the stack and see what happens. So first, we have a bunch of garbage bytes. And the garbage bytes overflow name. They overflow the SFP of vulnerable, just like in a classic buffer overflow attack. But instead of overwriting the RIP with address of shellcode, we are now overwriting it with address of system. So now when the program wants to return, it's going to go to this address, which just so happens to be the instructions of system. And remember how we said when you go to system, how does system know where the arguments are? Where does it go to look for arguments? It goes on the stack. So in addition to writing this address, we can also write a malicious argument. For example, rm-rf. And now what we've done is when this program returns, it's going to go to system, and it's going to read this as an argument and cause malicious things to happen. So at a high level, this is the attack we're looking at. The two pieces we needed were overwriting the RIP to point at existing library code, like system, and then putting some additional arguments on the stack to cause system to do something malicious. So at a very high level, this is what it looks like. And coming up next, we'll break it down in some more detail.